Unit 14, Kinetics, and this video will go from pages 94 to 102 and corresponds to Moodle Quiz 1. So, first of all, kinetics focuses on the rate at which a reaction proceeds. So, a rate of reaction calculated or measured over an interval of time is called an average rate of reaction. So let's consider this reaction where A is making B, and in this reaction it may be happening at a slow rate or it could be happening at a very fast rate. And A is disappearing while B is appearing. And so the rate of reaction for B is going to be, this is positive, meaning it's appearing, and it's going to be based on the change in the moles of B over time, whereas the rate of reaction for A is, this negative is just representing that it's disappearing, and its rate is going to be based on the change in the moles of A over a change in time. Rates of reactions are always positive. Consider the experimental data measured for the reaction 2A to 3B. The average rate of reaction at each time point is calculated in the table below. Notice that the average rate changes as the reaction proceeds. So you have two tables, and here we focus on the rate at which B is formed, and in this table we focus on the rate at which A is disappearing. So notice that over time, so here's at time 0, and we have all reactants and 0 products. But as time progresses, your reactants A is slowly disappearing while our products B is appearing. And so you can determine the rate at which this is occurring if you take the change in moles divided by the change in time, and then you get the rate. An instantaneous rate is the rate of a reaction calculated or measured at a specific instant in time and is called the instantaneous rate of reaction. The words rate of reaction usually refer to the instantaneous value. So if we look at this graph, we have time versus the moles of our product. And here, over time, you can see how the reaction is proceeding. Notice that it gets a little, your moles of product being formed gets a little bit less and less as time goes on. That's because eventually the reaction will reach completion. If you were to take the tangent or the slope of the line at a specific point in time, then you can find out the instantaneous rate at that time. Generally, we don't really focus on the instantaneous rate, but more the average rate over time instead. Using chemical equations to compare rates of reaction. Rates of reaction are going to be related by stoichiometry. So the rate in the figure below of 2 frames per hour to 8 tires per hour has the same relationship as a 1:4 ratio. So here you take 1 car frame plus 4 tires, and over however much time it takes, this reaction is complete once a full car is made. And so we have the stoichiometric coefficients, 1 car per 4 tires equals 1 car. So rates of reaction are related by the stoichiometry. For the general reaction as follows, A, B, C, and D, the coefficients represent the stoichiometry. The average rate of reaction for reactant A would be equal to, and this is only it's only a sign to represent that it's disappearing, not necessarily that it's a negative value. But it's the change in the moles of A divided by the change in time. The rates of reaction are related by stoichiometry in this way, that we have 1 over the stoichiometry times the rate is equal to 1 over the stoichiometry times the rate of B is equal to 1 over the stoichiometry times the rate of C, which is equal to 1 over the stoichiometry times the rate of D. So this right here is note card worthy. And notice that our value here would be in the denominator next to the change in time, would represent the stoichiometry for each of these reactants and products. The negatives tell you it's reactants, the positives tell you that it's products disappearing and forming. So let's look at example 14.31. The rate of formation of cars is 0.116 cars per minute. Calculate the rate of removal of tires from the rate of formation of the cars. So here's the equation. 4 tires plus 1 body yields 1 car. And so we will take our 0.116 cars per minute, and we'll use the stoichiometry that for every 1 car, we remove 4 tires in order to get the rate of removal of the tires. So 0.116 times 4, which is equal to 0.464, and that's going to be tires per minute are removed. Example 14.32. Determine the balanced reaction that has these rate equations. And so here's our rate equation. And recall that the little negative symbol is going to tell you that these are reactants, and that positive tells you this is a product. So I know my reactants are N2 plus H2 yields NH3. And then this value in the denominator next to change in time is going to tell me the stoichiometry. So it's a 1:3:2 ratio. So a 1:3:2 ratio. And so this would be the balanced equation that has this rate. Now let's look at rates and concentration. Rates are represented by what's called a rate law. And a rate law is going to give you the rate of the reaction, K, which is called the rate constant, and then each of your reactants, which are placed in brackets because that represents the concentration of the reactants. And then there's a little symbol here, which is an exponent. We have M there, we have N here, and those exponents represent what's called the reaction order. This reaction is said to be at the mth order for reactant A and the nth order for reactant B. And if you take the sum of these two, add them together, you would have what's called the overall order for the entire reaction. So for example 14.33, determine the orders of reaction for this reaction A plus B yields D with this experimental rate law. So we're given rate is equal to K times A to the first order over B to the second order. It's going to be easier to go ahead and move B up into the numerator, and so what that makes this is rate equals K times A to the first order, and moving B up to the numerator changes this 2 to a -2. So the order for A is the first order, B is to the -2nd order, and to find the overall order, we'll take the sum of the order for A plus B, which is going to be 1 plus -2, which gives you an overall order of -1. Example 14.34, determine the orders of reaction for this equation with this experimental rate law. So rate is equal to the rate constant times hydrogen and bromine to the 1/2. And so the order for hydrogen is equal to 1, it's to the raised to the first order, and the order for bromine is equal to 1/2 based on the exponent, and then the overall order is going to be the sum of these two values, 1 plus 1/2, which is equal to 3/2. Mechanisms of a reaction have two categories: elementary reactions and complex reactions. Reactions that take place in a single collision of particles are called elementary reactions. For an elementary reaction, single collision, such as this, the orders of the reaction in the rate law are the same as the stoichiometry. So, because this has a coefficient of 1 and this has a coefficient of 1, that's how we know that the rate law can be written rate is equal to the rate constant times bromine raised to the first order and hydrogen raised to the first order. Most reactions are actually very complex and are composed of many elementary reactions. The complex reaction, H2 plus Br2 yields HBr, really takes place in a sequence of elementary reactions as follows. And so because there are several reactions that occur, you cannot use the stoichiometry in a complex reaction to identify the order. In complex reactions involving more than one elementary reaction, the rate law is often more complicated than the simple stoichiometry implies. Finding approximate rate laws for complex reactions, in some cases when the rates of elementary reactions differ by several orders of magnitude, the rate law simplifies to the rate of the slowest step. Because the rate of the reaction is determined by the rate of the slowest step, we call the slowest elementary reaction the rate determining step. And so we want to always look for the slowest step, and that will be the rate determining step. Here's an example. The two reactions given here are elementary reactions that together form a complex reaction. The first one occurs the slower, and the second one occurs fast. The first reaction is the slowest, and this will be the rate determining step. So we write the rate law based on the slow step. And so we will write the rate is equal to K times the concentration of A plus the concentration of B. And each of these are to the first order because they have coefficients of 1 and 1. And so here's your rate law. Here's a second example where you have A plus B goes to C, that's your fast step, and then you have 2C, which is your product, that's your slow step. The second reaction is the slowest, and this will be the rate determining step. And therefore, you would write the equation as such. The rate is equal to K2, the rate constant for the second reaction, times C raised to the second order because there was a coefficient of 2 here. Now you can pause the video and copy the notes from the note card given here that summarizes everything that you should have gained from this video. Rates are dependent on stoichiometry. When you write a rate law, the rate is equal to K, the rate constant, times the concentration of A raised to its order times the concentration of B raised to its order. Orders are not based on stoichiometry. The orders can be determined in an elementary reaction by using the stoichiometry. You cannot do this for a complex reaction. In a complex reaction, you should be given a series of steps, and the rate law will be based on the slower step.